Okay, so first quick recap what happened in the last lecture. So we studied covering spaces and what is the role played by fundamental group. So in particular, we showed that when X and so X and both X and its cover are path connected, then so we have a covering map. And so we show that this the preimage of any point. So there is a bijection between preimages of any two points X, and so this can be interpreted as a number of sheets in the cover. So in particular, the same as there's bijection between this set and the set which describes the decomposition of evenly covered neighborhoods here into open subspaces here. And so we also showed that there's a bijection to the following set of cosets of y1 of x, the fundamental group of x. So I can fix some base point here, and it's lifted to some fixed base point here to the quotient of the subgroup H. So H is a subgroup which is an image of pi1. It's still there on the push forward of my projection P, and we also know that this is injective. P star is injective, so this is also isomorphic. The subgroup itself is isomorphic to the fundamental group of X tilde. So before we showed a certain lifting criterion for lifting the maps from. There was before we had a few lectures ago. We considered a situation when there was a map from y times interval to x, and there was a condition. We showed that there is if we fix the value. If we have so we consider some map f here, and we fix a lift of this map restricted to the beginning of the interval, this uniquely determines lift on the whole product. And now we want to use this kind of what we learned. We want to use it to describe a more general lifting criterion. And we formulated as the following proposition. So in particular, we mostly use this statement to when the case when y is a point or y is an interval, but to use this statement about this situation to have a unique lifts of paths and unique lifts of path homotopes. Okay, so assume topological space Y is path connected, and what is called locally cross connected. I will define in a moment what this means, but you can guess more or less by the name what you can expect. So if these conditions are satisfied, there exists a lift. So the first proposition will be about existence, and then we show the third proposition about uniqueness. You lift F tilde in the following diagram. So suppose I have a map y to x, which I want to lift, and there is a covering space x tilde, and so I want to fix base points everywhere. So in particular, I want to fix base point here x0, and as before, I want to fix x0 tilde here, so that this is projected to x0, and I also want to fix a base point here y0, so this is mapped under f, it's mapped to x0, and now so you will be asking a question about the existence of a lift f tilde from y. This will be a map from y to x tilde such that in particular this base point is mapped to x0 tilde. Okay, so this is the lift if and only if, this is a criterion, so it is the condition if and only if, the image under push forward of F of the fundamental group of Y is inside the image of the fundamental group of x tilde in X. So both of these guys are subgroups in the fundamental group of X. So now, as promised, I want to tell you what star means. Some technical assumption which you'll have to use. So a topological space Y is called locally fast connected if any point Y and any neighborhood U of this point Y, there exists an open neighborhood V. This is also neighborhood of Y, which is contained in U such that V is fast connected. So this is kind of locality means like we can have arbitrary small neighborhoods. For any point there is an arbitrary small neighborhood which is fast connected. let me know that locally path connectedness and path connectedness they don't follow from each other. They are independent. But if you don't make any other assumptions there, one of them can be true while the other is false.
Which kind of assumption can we put for one to imply the other?
If I'm not mistaken, if you can imply connectedness and local path connectedness, then it implies path connectedness. Okay, so let us prove this criterion. So this is so first let us prove in this direction. So this direction is easy. So suppose we have a lift, and we need to show this. So the lift means that there is a F. In particular, means that the following. So this diagram is commutative. So F is obtained by this composition, and this means so if I take the push forward of the left and the right hand side, this means that the push forward of F star is a composition of push forward of P and push forward of F star, and this of course implies that the image by star is inside the image. Okay, so this part is easy. And the second part requires a bit of work, so we have to show the existence. So we need, so we will do is actually construct, give a construction of this map. Tilde. Okay. So we want to construct so we have some map. So we have some space Y. There's a map to X. Tilde. So we know that locally X tilde looks like a bunch of copies of X, and tilde. So there's some base points fixed everywhere. Y0 here, X0 here, and 0 tilde. And let me take some point Y, and we want to construct. So we want to define F tilde, we want to define so alpha for any point Y. So let me take some point y in here, and so y is path connected. This means that there exists a path in y which connects y0 with y. And I can of course make a composition of this path with f. So we have f, and give me some paths. The composition will give me some paths. From x0 to f of y. Path in x from x0 to f of y. And so we know how to lift paths, right? We know that if you fix the starting point, there exists and there is a unique lift of paths. Unique lifted paths. Composed with G tilde, such that well, it starts. We know it starts. If we want uniqueness, the condition that it starts at x0. There is some path. We can lift this path. This lifts somewhere. And so essentially what I want to do, now I can say, okay, this is where I lifted the path. The endpoint of this path is going to be my value of f tilde. So because we want, we want if such lift existed, we wanted it to be commuting with this lifting of path operation, which we do, right? So we want this to be the same as the composition of lift of f and lift of g. So we can just define. So what we want is what we want to define. Well, let us define this kind of our wish, but now we're just defining f tilde by the following formula. So y, the image of y is the endpoint of this path. Okay, but of course we need to check that this is a self-consistent definition, and it's also we also need to check that this is a continuous map, and this is indeed provides a lift of f. So first, this definition requires a choice of path G here. We want to show that it's independent of this choice of my path G. So okay, let's take some other path, G prime, and see what happens. Are we going to get the same result? So of course we can take other G. Path Y, which starts from Y0 and ends at Y. And so of course this will be the composition again will be some other paths from x0 to f of y, and so you can consider the following now. Then I can consider the following composition of paths. I go first like this, and then I return in the opposite direction of this of my new path. Consider H to be the following composition. So first go along the path FG, and then consider composition of G prime with F, and take its inverse. So this is a loop in X based at X0, and so of course I can also rewrite this. This is the same as first taking composition of G, path G with G inverse, and then taking the composition with F. And so in particular this means that H is a loop in X based at X0, so it represents some element in the fundamental group, and due to this expression, it's certainly in the image by definition of the push forward. It's certainly in the image of the push forward of F star of the fundamental group of Y. Right? And we know by our condition in our proposition, we know that this is a subgroup inside the image of P star. But we know we had when I considered this subgroup, there was a proposition which gives explicit description of this subgroup. What is the element of this subgroup as which elements in the fundamental group of X are live inside this subgroup, and those are elements which are lifted to loops in the covariance space, right? This means H lifts to a loop. Loop in X tilde based tilde. This is a criterion for elements to be inside the subgroup, which we proved in one of the propositions last time. And so we know that this lift is unique once we fix the base point. But we can also, so this means that I can also obtain directly a lift by lifting those guys here, right? this lift should be the same if I do the following composition of lifts of these two paths. And so this is a here. Well, this is a particular. This is a lift which starts at x0, and then this is a lift. Well, I can write it. I should better. I can write it like this. So it's actually the same. And then I lift this, saying this is a certain lift which starts at the same endpoint. At the endpoint of this lift, which is this point, and we know that this is a loop. So we know it's that this guy must end, if it starts at the endpoint here, it must end at x0 tilde, this guy. But this is, if I inverse this path, this means that this lift, the inverse lift, starts at x0 tilde, and must end at the same point as this guy, which is this. And this shows this indeed verifies independence. Independent of choice of G. The picture of what happens here is that we consider some lift. A certain lift of the inverse of this path, which starts here. So in general, it could end somewhere not at x0, but since we know, because of this condition, we know that it should be this composition. We know that this composition must lift to a loop. So we know that this must end the lift of f prime tilde g prime inverse must end here. But then it means I can just reverse this path to show that if I lift it starting from this point, it will end, it must end here. I'm just repeating what I said here. It's clear. Any questions?
Why the lifting of two product, the concatenation path will be the same as the product of the
Why the lift? Well, this well, I mean, if you have, so you want in general, if you have something like G1, concatenation G2, why this is the lift of this is this. Well, because, I mean, you can check that this, I mean, this is a sum lift. I'm talking about sum lift. I mean, the lift is unique only when we fix the stack. So we can just check by the formula of composition. You can just, I mean, the lift is something which satisfies this condition. If you I mean, you can just check by the form of the composition that this is, because this is just given by parsewise this composition. Yes, it's something like this. G1 of 2s, sorry, G2, 2s, and then G1 of 2s minus 1. So if I want, if I put lifts of these guys, this will satisfy this condition. But of course, I mean, this is a sum lift. So here, I need to, this is sum lift. So suppose I fix, to make it unique, here I need to fix it, to make it unique, I need to fix G2 of 0 here. G2 of 0 here. And to make this unique, I need to fix such that the starting point here is such that G1 of tilde of 0 is the same as G tilde 0 of 1. So I fix G2 0. So here I have a particular lift which.
Is there any topological assumption on X?
On X, no. No, the assumption was on Y. But of course, I mean, the fact that Y is path connected and F is a continuous function gives you some constraints. Well, I mean, yeah, there are assumptions only. We impose assumption. Sorry, I don't know.
So if I understand, the fact that we choose it to be a core will define the function f theta.
Yes.
We choose it to be the same. We want to prove that they are the same, and we choose it first to be the same.
What do you mean?
I mean the G prime, and I mean the endpoint of the.
Okay. Well, we show that. So what? So okay, this I mean, we have some paths here. So what we want to what we show. So what we do is the following: is that so first there's we make a observation that if we consider a loop obtained by this composition, because of the condition in our composition, it must lift to a loop here. But the other way to construct this lift is to construct first a lift of this guy, which we already have here, and then lift the inverse path here. So this will give me some lift, which is unique once I fix this point. And we know that this must lift to a loop. So we know that if you consider a lift of this guy, starting from this point, it must end at x0 tilde. And then, of course, by similar argument, just by explicit definition, we know that the lift of inverse is the same as inverse of a lift. once we specify this point. So if there is unique, so then we know that if you consider inverse this lift, this provides a unique lift of this guy starting at this point. And we know that it ends here. This shows that the lift of this guy, indeed, starting at this point, ends here. Is it okay? I mean, you can also make some sort of just prove it if you want, which prove it like by contradiction. Assume you have some lift, it doesn't end. I mean, it's lift starting at this point and ends at some different point here, and then arrive at some contradiction by using similarity. But the important ingredient here is that the uniqueness of lift paths, which we saw before. Okay. Okay, so we showed that this function is well defined. And we also want to show that it's continuous. So consider U. So we have some point y, and so consider U a subset in X which contains y, which is an evenly covered neighborhood of y, and so we know by it's evenly covered, so this means that any sorry, this is not y, this is neighborhood in X, so this is F, contains F. So evenly covered means that it's lifts to a disjoint union of open subsets in X tilde such that by projection E they are homomorphic. Each of them is homomorphic to itself. And since we know that they are disjoint, there is unique. There is only one of them, which contains the value of F tilde of y, which we already constructed. So this is already unique with them. It exists unique U tilde. Such that so this in X tilde such that P restricted to this U tilde provides me with a homomorphism to U. And I want to, of course, you want to use the fact that the original function was continuous. So F is continuous. And we also know that y now we want to use this technical assumption, is locally path connected. This means that, so locally path connected in particular means that, so, I mean, f is continuous. This means that we can find the neighborhood of y, open neighborhood of y, which so that this image is inside U. But for any neighborhood of y, we can always find a smaller open neighborhood, which is locally path connected. You can always find locally path connectedness implies that there is a small enough neighborhood of y, which we call V, which is mapped inside U. Which is path connected. So there exists V neighborhood, open neighborhood V, such that in Y such that its image is inside U. So this is where we use use continuous, the fact that f is continuous, and by using locally path connected, we cannot choose V to be such that this is trivial. Sorry, no, sorry. This is such that V is it's V is path connected. I'm not using.
What condition has to have U tilde?
I'm not using. Well, I'm not here in this part. I'm not using U tilde. I mean, so what is the question? Here, this is a statement just here. I mean, I would like to use the fact that I chose U to be evenly covered.
But why I need U? Why uniqueness in the?
For this part, I don't need this so far. I'm not using this so far. I will use it by so in a moment. I will use this. So in this statement, I'm not using U tilde.
But in the definition of evenly covering, it's each sheet which is such that the restriction should be homeomorphic to.
Yes. The many. Well, if you want to make it more explicit, P1, so P inverse of U is a bunch of. Joint union of some U alpha, and U tilde is U alpha for some alpha. There exists unique guy here which contains.
That's what you didn't write.
Yes.
F tilde.
Yeah. Well, okay. I didn't write, but I said it in words. Are you happy now? Sorry, I forgot this picture. Okay, so V is path connected. This means that there exists so for any for any y prime, or maybe my life to be hard, so I take some y prime, another y prime in this small neighborhood, and I take a path from y to y prime. For any y prime, there exists a path L in V from y to y prime. Of course, I can compose this path with f to produce some path here. And okay, but I also, okay, let me, so I can do the following. And compose G with this L, so L, position of L with G is a path from y0 to y prime. Just composition of these two guys. And so I can, if I want to calculate a value of y prime here, I can calculate it in this way. I can calculate, so I can be sure that I can choose any path from y0 to y prime. So in particular, I can choose this composition, and so by construction of my f tilde, so this is so I want to consider this composition of the composition of paths with f, so this gives me some paths here, and then I lift it, and then I calculate its endpoint. But of course, this can be also understood. Again, I can consider lifts of compositions instead. And so we know that this is some lift. I can make. So there is unique lift of this guy, and I can just realize this lift because if restricted to U tilde, where this f tilde, where the endpoint, if I restrict this to U tilde, which contains the endpoint of this path, there is a homomorphism between this U tilde and U, and from uniqueness, this lift is the same as just by taking this the inverse of P restricted to U tilde. So this restriction I can inverse and composing it with F and L, right? And so this means that this means that this path will stay since I chose my V to be inside the image of V to be inside U. This will be inside U tilde. This path will stay inside U tilde. In particular, its endpoint will also be inside U tilde. showed. So we did it for any point in V. This means that the whole V is mapped inside U2. And this implies that F tilde is continuous. Because, of course, for any neighborhood of image here, I can realize as U tilde, as U tilde for some U. Well, okay, so this shows continuity, and well, the fact that it's indeed the lift should be obvious, because you want to check that indeed this composition is F. So let me take some Y, the value of this composition of Y, so this is P of this lift at 1, but well, by definition of the lift, this is the same as F. Its composition as P is the same as the endpoint of just this composition, which is indeed F of Y. Okay. Questions?
Why any open set in X tilde can be realized? I mean, each point has a neighborhood which is kind of the image of one neighborhood in X.
Oh, wait. Well, if I take my neighborhood, well, if I take some point here, I can always assume that, sorry, I can always suggest some point here, it's projected at some point here, so I take a neighborhood here, and I can always take a neighborhood such that it's evenly covered.
So the projection is always open?
Well, I mean, we know that we use this the fact that this is we have this adjoint open sets. If I fix my point, if I consider a particular point, there's a unique open to alpha here. I can always cover, I mean, for any point I can choose like any point inside an open set, I can choose U alpha. We've been in this for always. so okay, the next proposition will be about uniqueness. And it's unique. So let F1 till there and F2 till there be two lifts of F in the following diagram. And so now we are assuming Y to be just connected. So for this uniqueness property, we just need a weekend condition, just being connected. And the statement is if there exists Y, point Y in topological space Y, such that the lift coincides, the value of the lift coincides at this point, then this implies that the lift, these two lifts are the same everywhere for any point. The value for any point is the same.
I have a question about the previous proposition. So this proposition means that if we take the identity, for example, in S1, and the cover XR as a covering space, then it's not possible to lift the identity.
Yes.
But it's look like if we take this.
Well, I mean, so you want to get the map from S1, and here you have R. So the identity, you're going to send identity as a kind of pass going once around here. For one point here is various point here. But if I start lifting it, I cannot do it like this. Like if I want to make sure that my function is locally continuous, so I have to do like this, and I will end up that it must be discontinuous at least at one point. There is no way to, well, in this case you can just make sure, you see there's no way to kind of continuously embed this one into R. Yeah, after this position, I will consider a simple example of how this works. Okay, so how do we prove this? So again, for any y, let me take any point y here, and the is evenly covered. U the pre-image of U is the disjoint union of U alphas, and so we want, so this is so since the disjoint union and there will be a unique point if I fix my so since f tilde, so the projection of f tilde 1 of y is the same as p of f tilde 2 of y, the same as f of y. There exists a unique of 1 over 2 in this decomposition such that fi of I is just 1 or 2, y tilde 1 is contained in U alpha I, which is false one part of the adjoint. And sorry, what? So again, so we want this U to be, of course, this is contained U such that U which contains f of y, so U is in X. And so we also know that they're continuous. This means that they exist open neighborhood B inside Y now, which contains the neighborhood of Y, such that for both of them, so you can always take individual for each of I, but then we can take intersection. So we can choose Y such that for both I equals 1 and 2, f tilde I of V is inside the corresponding open set here. So now, I mean, there are two cases when these two guys from this decomposition are the same, or they're different. Well, they can be the same. Well, let me first consider the case when these two values are different. This implies that these two guys are different, so they cannot, because we know they're not intersecting. And so if they don't, yeah. So in particular, we know, because we chose V like this, we know that the values for any y prime in V, the values are different, right? Because this guy is like disjoint. And okay, so before we proceed to the second case, so maybe we can define a subset in Y, subset of points where the value of f tilde 1 and f tilde 2 is different. Right? And this argument showed that, sorry, this was of course not equal. This is not equal. But if they were equal, this means that they intersect and they can't. This is not equal. So we choose, so this was, y was a particular point in this subset. And this shows that there exists, we can always choose an open neighborhood V. So this is also true for any point in the open neighborhood V of y, this is also true. This implies that this whole set is open. The second case, consider, now consider the case when they are the same. This means these guys intersect at one point. So this might be the same. And similarly, this means this the lifts must be the same at any y prime in V. This is because, so how do we show this? Okay, this is something we need to show. And so this is because, so we know that well, the lifts of the same function f satisfy this condition that the composition with p gives me f, and we know that p, if I restrict p on this, well, let me denote this just by alpha now, because they're the same. We know that p restricted to u alpha is a homeomorphism to u. And so in particular, this means that if I restrict it, so if I can, so we consider points y inside V, they automatically, the values of f tilde, they live in u alpha. And we know that this is if I restricted p to u alpha, it becomes in particular injective. So it's injective. This means that this condition implies this. So this is indeed true. And so now I can similarly define B to be a subset, another subset in Y, which is a set of points where the values of two lifts are the same. And similarly, so since we know, so we started with, if we start with some point y, some fixed point y, this is which belongs to this set, we show that there exists an open neighborhood V, so this is true for any point in this neighborhood. This means that this is open. But of course, for any point, either the values are the same or they're different. This means that y is, so combining these two cases, so we learn, first of all, we know that y can be understood as a union of A and B, which are also by the construction they're disjoint. So, what I'm saying is this is the disjoint, and A, B are both open. And we also know from the conditional theorems, we know that there is at least one point in B, right? Because we know that they coincide at one point. We know that B is non-empty. And we also know that this is connected. So the only way for this to work is that when this, the whole thing is just A is empty and the whole space is B. Because otherwise it will be a disjoint union of proper open subsets. Questions? Let me, to make it kind of less abstract, let me consider a simple example of how this works. And so let me consider the following case when x is C star, which is C minus an origin complex, set of complex numbers minus origin, and x tilde also C star. Now we consider coloring map the following. So this is from map from C star to C star, and I'll define by, if I take a non-zero complex number here, I send it to some power. Integer power. Yeah. So this is a punctuate plane. You can easily see that this cover has n sheets. Because locally any the preimage of any point, the preimage is corresponding to taking a square, sorry, nth root of some number. And we know that this is non-zero, they're n distinct, n distinct roots. And so let me consider, for example, what do you want? Consider F, let me some maps from S1 to C star and ask a question when they can be lifted. To C star. With respect to this, with respect to this coloring. sense this equation can be, like if you have some map from S1, can we globally take its nth root of this function, so that it's continuous. It's still a continuous function. And so for any so any map. So what we're interested is, so suppose this, well, this takes, so this as before, let me represent it as R mod Z, and so this takes some point T to f of T, this is defined model 1, and so what we're interested is what is f star, what is push forward. So here we know that it's Z, and here we also know that it's Z because this is homotopically equivalent to S1, right? Because we can always deformation reduct it to a circle, for example, to unison circle. Well, this is a homomorphism, so it's just determined by the value of a generator. Yeah? And geometrically, this generator, so we have a map from S1 to punctured plane. So geometrically, what this M corresponds to is how many times the image winds around the puncture here. And you can calculate it if you're familiar with this, maybe from complex analysis. You know this actually can be, in terms of f, it can be explicitly calculated as follows. For example, using this integral. And we also know, so so P star is also a map. So is a map from fundamental group of x tilde to fundamental group of x. And so we know this is both of the spaces are C star. This also will be a map from Z to Z. And it sends 1 to M, right? F. So P of Z is M. So it's easy to see if I take a generator in x tilde, or x tilde is the same. So if I take some generator, it's plus corresponding to a generator in the fundamental group. Here, it's just a loop which winds once around the origin, and this will be, its image will be a loop which winds nth times if I apply this composition. If I compose it, this is the end. And so the criterion was that there exists a lift of f. So of course it's easy to see if this is satisfies all this condition. So x, it's path connect. S1 is path connected and locally path connected. There is the lift of f if P star. Sorry, is some subgroup in Z is inside the subgroup which is P star. This is also subgroup in Z. This is X. And this we know, this is M, Z. The subgroup generated is by multiples of M. And the subgroup generated by multiples of M. And this is the case if M, let's see, one of them divides the other. So this is M divides M.
Not the inverse.
Well, this should be a smaller number. You agree? In other words, here there exists one can globally define if this condition satisfied. Globally, in the sense that one can choose for any t, one can choose a particular branch in the nth root. So this is a still continuous function. So because this is a very easy example, one can arrive to the same statement without using this generic theorem, just illustration how it works. There's a more complicated case, you don't have this easy geometric. I mean, in the harder cases, maybe easier to work with the algebra than just looking and trying to visualize what happens. Questions? So yeah, it's time to finish soon, so there will be no time. Yeah, it's just to go for the next position. But so let me announce. We don't can announce what will happen next. So we can ask the following question. So we know so we learned that for any covering defines a certain subgroup in the fundamental group of our space. I want to ask the question: if you take some subgroup, is there always exist a covering space corresponding to this subgroup? So namely, if I take some hash y1 of x. Say with some fixed base point. The question is there exists a covering T such that we will see that the answer, under certain assumptions, the answer would be yes. But before solving this more general problem, we would like to solve the following problem. Consider first the case when H equals 1. So can we is there always a covering space which gives me a trivial subgroup? And such covering spaces has a special name. And following, so let me write the following definition is simply connected covering space of tilde is called a universal cover of X. Because this is the covering space being symplectic is the same as this condition, because we know that this is in general this since P star is injective, we know that this subgroup is isomorphic to pi 1. So requiring H to be trivial is the same as requiring X tilde to be simply connected. So later we will learn why it's universal. And yeah, next time we will show that under certain assumptions on X, there always exists universal. One can construct a universal cover by providing an explicit construction. But for today.